Welcome to the penultimate session of this workshop, and the first talk is by Ranjan.
Okay, thanks Swagat for the sharing the session. Okay, first of all, I would like to thank the organizers for inviting me to this exciting conference. I have learned quite a few things in the times that I've attended, the talks I've attended. I'd like to thank all of you for coming to my talk. So I'll be talking about some things that I did sometime earlier on how to search for dark matter and dark sector particles using gravitational waves. So I'll have three different parts of my talk, and I know that the audience is quite broad, from undergraduate students to postdocs to senior faculty members. So I'll make the talk in a very colloquium style. I'll not talk of much details, but I'll be happy to talk offline about the details. I mean, all of these works, as I say explicitly, have been done by my collaborators, and it was a pleasure for me to just sit and learn. That's it. Okay. All right. So let me start from the basics. So this may all the seniors know, but let's do it for the juniors. So we know that we need new physics, right? So the standard model of particle physics and lambda CDM cosmology is excellent in explaining the smallest structures of the universe, standard model, the particles, and lambda CDM tells you the largest objects of the universe, right? However, there are many questions which gravitational waves can potentially answer. For example, what is dark matter? This is a question which gravitational waves can answer. I'll talk about it. This is work done by Sulogna, the audience. And then what is dark energy? This is probably also can one do. Or also, are there new forces in the universe? This is also something I'll be talking about. And then there have been extensive discussions on how we can understand about various phase transitions in the universe using gravitational waves. The bottom line is that gravitational wave observatories are a new probe, and they may provide answers to these questions. Okay, so this is a figure that I took from one of these reviews by Bertoni et al. In 1907. This is a bit old, but it's still applicable. So what in this the figure that they showed how gravitational waves can probe various kinds of dark matter scenarios. Obviously, it can probe phase transitions, it can probe primordial black holes, it can probe environmental effects. That just simply means when the black holes are merging or when the neutron stars are merging, they are moving through some medium, right? And you can actually measure that in gravitational waves, right? For example, the merger rate, dephasing light dark matter clouds, exotic objects, like if you have things which are very compact, which can give strong gravitational wave signals, but cannot give, but are not black holes or astrophysical objects, you can measure them. Again, you can have direct searches, right? This is something I'll talk about. Gopu talked about pulsar timing array, using interferometers, and then you can also probe perturbative dark matter production, right? So in bottom line, I mean, gravitational waves can actually do a lot of things about dark matter. And they also had this plot, which is I think very nice, which in the x-axis, what is plotted is the dark matter candidate mass, right? So the lightest mass that a dark matter candidate can have and make up 100% of dark matter is roughly 10 power minus 22 eV, right? Electron volt. In case you are more of an astrophysicist, one solar mass is 10 power 57 GeV, right? So this is extremely small, right? Electron is half a MeV. And the heaviest mass dark matter candidate can have, so this question is a bit subtle to answer, but anyways, it can be a few tens of solar masses, right? And I can tell you later where is the subtlety, right? And as you can see, there are lots of different candidates, well-motivated candidates, which gravitational wave can measure, say axion dark matter, axions, dark photon dark matter, PBH mergers, and things like that, right? PBH and subvelo transits and things like that. Anyways, so I'll come to that. As I said, the three parts of my talk. The first part will be probing dark matter and nucleon cross-section using transmuted black holes. I'll tell you what these are. The second part will be how to probe long-range forces coupling to muons using neutron star systems. And then finally, there's something which I have actually not worked on. I've just read how one can directly detect dark photon dark matter. All right. So this is the first work. This is the work I did with many people. Sulogna is there. She did everything in this work. And in this paper, Anupam did everything, right? I was just learning. All right. So what's the idea? So let me say it. Sulogna gave a talk last week, but in case some of you are not around, let me just rephrase it. So this idea is very old, and we just sort of did it in a newer context. So as you have two neutron stars, they are moving around in a galactic halo. All right. So this picture, right? There's a galactic halo. Neutron stars are moving around in the galactic halo. If the dark matter and neutrons. So let me just assume that there is only coupling between dark matter and neutrons, right? You can also coupling with other particles. You can do these things, but let me just assume that if the dark matter and neutrons have a non-zero, non-gravitational force or attraction or interaction, what can happen is as the neutron star is moving through the system, the dark matter can collide with the neutrons inside the neutron star. In that collision, it's a two-body. So what I'm talking about is a two-body collision. Dark matter neutron goes to dark matter neutron. In that collision, there is a certain probability that the final energy of the dark matter particle after collision is less than the escape velocity of the neutron star. If that is the case, it gets captured inside the neutron star, right? So this can happen over the age of the universe. This is what I said in this first line. This can happen over the age of the universe, and you can show that for certain parameter space, by parameter space I mean the dark matter particle mass and the dark matter neutron scattering cross section, you can have enough capture such that these accumulated dark matter, which once they get captured, they get synced towards the center, are so much that they can form a black hole. All right. So there are some details here which I'm skipping. For example, whether the particle is a fermion or a boson, and then obviously there are additional assumptions. For example, as I said, I'm only talking of dark matter neutron scattering, right? And there can be other scatterings. I'm only talking of contact interaction. All of these things can be. There are lots of knobs you can change, but overall the picture is roughly the same. Once it forms a black hole, right? So these dark matter particles are sinking in, and if you have enough time, if the cross sections are large enough, these dark matter particles will collapse. This dark matter core that is forming at the center of the star will collapse and form a black hole. Once it forms a black hole, the black hole will eat up the entire star, right? Using standard accretion processes, right? In fact, you can show there's been at least two simulations that I'm aware of where they did this eating up of the star. That means you form a black hole at the center of the star and you calculate the time and also how much of the star is eaten up. You can show that the entire star is eaten up in a very short time. That's this time, T swallow, right? T collapse happened, and if this happens, effectively you have a black hole which has a mass of the neutron star. Note that you may ask, why is neutron star so special when neutron star is nothing special here? You can do this for any star possible. I mean, you have to tune the parameter space, but you can do it. For white dwarfs, you can do it. For sun, you can do it, but you have to go for different parameter space, particle dark matter parameter space. Anyways, now let's assume the thing that's happening is happening for a binary neutron star that were formed together. There are two stars formed in a binary, and then they died, they formed neutron stars, and that's the whole thing, right? If that happens, what we actually have is, again, two black holes which have the size of the two neutron stars rotating around each other. All right? So this is what we call a transmuted black hole. So this is not an astrophysical black hole. This is not a primordial black hole. This is a transmuted black hole. This name was actually first, as far as I know, given by Volodymyr Takhitsov in a paper. All right? Now these black holes will be roaming around each other, which have the size of the neutron star, which have the mass of the neutron star, and they can merge, and one can search for these signals. All right? And thus, as I gave you this qualitative idea, that this can give you a way to probe dark matter parameter space. A bit more quantitatively, you can ask for what parameter space, for what particle dark matter parameter space can this work? Okay, so let's talk about only this figure, and I'll tell the other figures are very similar, right? So let's go through this figure because there are a lot of lines here. So the x-axis is the mass of the dark matter particle in GeV, all right? The y-axis is the dark matter nucleon scattering cross section. More precisely, is the spin independent scattering cross section. Again, these are some particle phase details which does not matter. I'll be happy to discuss later. You see this line LZ2022. Anything above the line is ruled out. So LZ is also called Lux Zeppelin, is an underground dark matter direct detection experiments. So basically, they have a tank of xenon. Dark matter comes in, it hits the xenon lights up, and they try to find it. Right? I can tell you more details if you're interested. But anyways, so the region above is ruled out. Right? If this thing that what I said happens, then in this previous thing happens, then remember, if you ever find a neutron star which is very old, then they should not exist. They should be converted to a black hole. Right? Using this observation of this PSR-J, this pulsar, which is very close and also very old, something like 10 giga years old, you can show that this parameter space this anything above this line is actually ruled out by the fact that this PSR J04374715 is not a black hole. It's a very old pulsar and it's very near to us, so we know the dark matter density in that neighborhood very well, and we can do this. So any region above is ruled out, right? This idea that we had talked about, that if you have a binary neutron star, it becomes a binary transmuted black hole, and then you can search for the signal in LIGO. In fact, LIGO does this search in the context of searching for primordial black holes, for light primordial black holes, right? So using this data, LIGO 03 data, and assuming some binary neutron star merger rate density thing, Shlagna provided, is this region is ruled out, right, LIGO 03. And what we did is, obviously this limit depends on what is the exposure, that means the volume times the time of the search, and if you naively scale this by a factor of 50, if you increase the exposure by a factor of 50, which hopefully some future telescopes can find, so this entire region, anything above this dashed line, will be ruled out, right? Again, there are some astrophysical caveats, some particle physics caveats. I'll be happy to discuss that. And then there is this line explaining missing pulsars. So this is an old problem in astrophysics. Depends whether it's a problem or not. Depends on whom you ask. So some astrophysicists think that when you look at the galactic center, you don't find enough pulsars. Where are those pulsars? There are standard astrophysicists which will simply say that those pulsars are dim. So that's not a problem at all. But there are also some astrophysicists who say no, they should be seen. Anyway, so there's a fight between there, and there have been some studies saying that this idea, that dark matter converting a pulsar or a neutron star into a black hole, can explain these things. And so anything in this region, you can explain it, right? That's the idea. And then there's another line called the neutrino floor. This is actually connected to this LZ line. This is because of the fact that dark matter rejection experiments have already started detecting neutrinos, right? Both Panda X and Xenon have detected neutrinos. LZ have published detection of neutrinos. LZ has not yet shown it, but I know that they have also detected neutrinos, right? So at some point in the near future, neutrinos will be a background for dark matter detectors, underground dark matter detectors. All right. So this is the same plot, except that this is done for fermionic dark matter. Obviously, for fermionic dark matter, I mean, the collapse happens. The collapse thing is different because it's fermions, it's not bosons, so it can't come very close to each other. So obviously that's why some of the parameters are different, right? And this is if the bosonic dark matter that is collected at the center of the neutron star forms a Bose-Einstein condensate, right? Anyways, so the bottom line is obviously these things, there are some details, as I said, particle physics details, and also there are astrophysical details. But the point that we were trying to go for, just to show that near future gravitational wave detectors can be a new probe of particle dark matter, right? It's a new science case. Yes. Yes. So we, as far as I remember, we just took, so this is given by some other paper. We were not doing it. They just said it. But as I told you in the talk, that obviously some people think that this problem does not even exist. But this is some speculative thing, and we just said that this is a benchmark one can try. That's it, right? And to be honest, I don't think is a problem. But anyways. But the point is, see, this line is in some sense misleading. I mean, you can obviously, see, the point is the entire parameter space, say below here, is free, and you can probe it, right? So this is just a thing. All right. So one more thing, a few more things around this. So obviously, as I said, the black holes that are being formed, these are called transmuted black holes, have a mass function which is very similar to the neutron star mass function or the white dwarf mass function. So when we wrote this paper, this was the two mass functions that we could find, and here at least we were trying to say that at least if you find a subsolar means less than 1 solar mass, subsolar this one, if you find a subsolar mass black hole, it need not be that it is primordial black hole. One needs to check this thing, all right? Check this thing. It can also be transmuted black holes, right? It's again new physics, definitely new physics. Find a black hole which is 1 solar mass or below, but what kind of new physics? That's the question. And then finally, this is a plot I think Shlagna showed. What is being plotted on the x-axis is the redshift. What's plotted on the y-axis is the merger rate, and this is also another way to statistically distinguish a transmuted black hole merger from a neutron star merger from a PBH merger. So this thing, again, there are lots of details. but the idea of the plot is obvious, right? Primordial black holes, I'm assuming primordial black holes are dark matter, right? To be honest, I've forgotten what fraction we are taking, but it doesn't matter. It scales as 1 plus z cube, that's the important thing. So obviously, as you go to high redshift, the primordial black hole merger rate will increase, right? Neutron stars are formed from stellar collapse, so obviously, they should follow the star formation rate. And the star formation, if you know, it follows something similar. It peaks around between 1 to 3, and that's what it is. There is a slight delay because you form the star and then you have to form a neutron star and then it has to merge. So there is something called a delay time, and that's why it's a slight difference. It does not exactly track the star formation rate that people have measured extremely carefully, but it's roughly like this. It looks like this, and you can see this neutron star merger rate and PBH merger rate is completely different. Turns out the transmuted black hole merger rate is also different from the neutron star merger rate. Why? Well, first of all, not all neutron stars will be converted into a black hole. It will only happen if it's in a region where the density is very high. Two, it obviously depends on the particle physics parameter space, right? So this is the dark matter particle mass, this is the chi-n cross section. So obviously, if the cross section is lower, it will take much more time to form this transmuted black hole. So then obviously, this peak of the merger rate will be at much lower redshifts. It will not be at this redshift. Basically, what you're doing is you're taking this thing and then trying to convert it, right? So if this cross section is lower, you're capturing less particles, so it will take much more time. So that's why this peak shifts, right? And then obviously there's a long formula where you can do this. But the point here is still says that, I mean, if you can get this plot with real data, obviously this is a statistical way to do it. You can't do it individually. You get this thing with the real data, one can actually do lots of new things. All right, so this is thing. So the next thing I'll be talking about, so I'll shift gears completely and talk about how you can probe long-range forces. Again, this work was done by Jeff Dror, Tobias Fukuch, I was there, and the other work by Joachim Kopp, Tobias Fukuch, and William Shepard. I'll be talking about this work, but this is related. All right, so let me give you some basics, which many of you know, probably good for the students. Okay, so I've been talking about dark matter. Now I'll be talking of dark sector particles. I'll not talk of dark matter as such, but these are particles in the dark sector. Okay, so all of you must have heard about this GW170817, which was the binary neutron star merger that was detected, the only confirmed binary neutron star merger that we have detected with an electromagnetic component. So let's give some numbers because some of them will be useful here. So this is what it looked like. So this is the time and this is the frequency, and you can see this going up. It's mostly in Livingston. Fargo did not see it. Very well, Hanford had probably seen it if you see it very carefully. Anyways, so the component masses were something like this, about 1.4 solar mass. What you expect, the total mass of the system was this. It was found in one of these NGC galaxies, NGC 4993 if I'm not wrong, which is about 40 megaparsec away. And there was a near coincidence direction of a gamma ray burst, right? And the gravitational wave energy that was being emitted was something like 10 power minus 2, at least for this system, minus 2 solar mass. All right. So these are just some numbers that astronomers provided to us, and then you can try to understand this thing semi-classically. Obviously, gravity is super important, but here in this whole thing, I'll almost not use GR too much. All right. So all of you know this Kepler's law. So if M1, M2 are the masses of the two objects, and the delta is the separation between them, I'm assuming these two objects are point particles. This is the Kepler's law. You can also calculate the total energy of the system. This is the potential energy. This is the kinetic energy. All right. And then from GR, we know what is the power radiated via gravitational waves. Right? So this is a result from GR, d E GW dt is this. It depends on the on this mass mu, the distance between the two objects, and also on the frequency. And what GR dictates is that these two neutron stars are coming close to each other because the total energy loss is taken away by the gravitational waves. Right? So this is a cartoon picture, two neutron stars. They have an attractive force due to gravity, and gravitational wave emission is happening, so that's why they're losing energy and coming close to each other. So you can take this equation, you can solve this and connect the gravitational wave frequency to the angular frequency of this object, and you can roughly get this thing picture, right? So this gives you a rough idea of how the thing happens. What we were interested in, starting from this paper with Joachim, Toby, and Will, is how can we do any new physics with this thing? So there, we see one can do lots of new physics. We were trying to do something a bit crazy. What we realized, and not in this paper, slightly after this paper, is a result, nuclear physicists knew it for a long, long time, right? And particle physics did not know it very well. Actually, Raghu, who is in the audience, was one of the first authors who actually brought it to the particle physics community. The fact that neutron stars have a lot of muons inside them. right? And this is because of various nuclear physics processes, chemical equilibrium, charge neutrality, the fact that Fermi energy is 100 MeV, and the most important thing is the fact that the neutron stars have muons inside them, only muons, not anti-muons, is a pure standard model process. There's nothing to do with any BSM physics. Pure standard model, if you just do, you do weak interactions, if you do the equation of state, you get lots of muons inside them. And this amount of muons depends on the equation of state. So let's quantify this. So this is this paper, the x-axis is the neutron star mass, the y-axis is the muon mass fraction, right, in terms of mass. So these are these BSK, all of these things, these are various equations of state. So this tells you, if say this equation of state was real, just as an example, then if the neutron star mass is say 1.5 solar mass, then it will have roughly 0.5% of mass of muons inside the neutron star by mass, right? And this was this pulsar, this is the heaviest known pulsar when we are writing it, it's about 2.2 solar masses, right? So, so that tells you that at least in this pulsar, at least for this variety of things, so you can have a muon component which is as large as about 1% to about 0.1%. So think about it. So you can think of neutron stars as not just neutron colliders, you can also think of them as muon colliders. So 0.1 solar mass of muons are, I think I said it wrong. So 0.1% by mass, so 0.1% solar mass of muons are inside them and they're just rotating around in the sky. What do you do with them, right? There are lots of muons. In fact, so we did a very fun calculation. This is a larger number of muons than we have ever produced in the lab. You just do it. It's just an order of magnitude. Anyways, so we have lots of muons. Again, remember, pure muons, no anti-muons. What do you do with it? Well, so one thing we realized is because we did this previous work on this this was about using some dark matter. Let's assume muons have a long range force, right? There are many particle physics motivations for this, but we just assume that, right? If that happens, well, there will be two things that happen. One, in addition to the gravitational attraction, you will also have this new force, where Q1, Q2 are the muonic charges of these two muons, sorry, of these two muon populations, and this mediator is the mass of the mediator that is the mass of the force mediator between the two muons, m med, right? And this delta is the distance. As that Q1, Q2 is the muonic, and this is the mass of the. So we have assumed a U-cover force. If that happens, so in addition to the gravitational attraction, you can either have an attractive force or a repulsive force, right? Depending on a few things, because of what is actually technically the spin of the mediator, but let's forget those. And in addition to gravitational wave emission, you can also emit this for force mediator if it's light enough, right? You can just emit it. So in other words, the total energy that is, first of all, as I said, the force changes, and the total energy of the system, how it changes, is not just gravitational wave, but also is dipole radiation. This dipole radiation. No, that is not quadrupolar, right? Gravitational wave is quadrupolar. This is dipolar, right? So more precisely, what we did is we used something called L mu minus L tau force. In case you are not familiar with this, so let me explain it in a minute. So L mu and L tau. So these are muonic lepton number and the tau lepton numbers. And turns out these are one of the very few extensions of the standard model that you can do, which is anomaly free. By anomaly, it means if you do loops, you don't get infinities in one sentence, right? So we took an L mu minus L tau force. Why? Well, because if you take a Le minus L mu, well, matter is made of electrons, right? I mean, the fact this is made of electrons, right? So then you can have laboratory constraints. There are not many muons and taus in the universe. So that's why we took this L mu minus L tau force, all right? So this is just to be what is plotted is the gauge coupling on the y-axis and the vector boson mass on the x-axis, right? Note that this is extremely small in order to have this thing work. And what we did is, if you do this entire calculation, what you can show is because of this energy loss channel and also this new force, the amplitude of the signal changes. And in this work, what was done is we took some results from Nicholas Yunis, who actually compared something using our older result, the paper with Joachim and others that we had, and showed how having a new force, how you can sort of probe how you can do sensitivity curves for new forces. So as I said, basically what happens is because of these new emission and the new forces, the strains change, and then basically what we did is we took at that point whatever was the LIGO sensitivity, and we tried to probe what part of the parameter space will be ruled out. Okay. So let me explain this a bit more detail. As I said, this is the vector boson mass, this is the gauge coupling. So let's think of this line, thin line. So these two thin lines that you see are for the pessimistic muon fraction. That means the muons are about 0.1% by mass. And these two thick lines that you see are for optimistic muon fraction. That means muons are 1% by mass, right? Anything above is ruled out. So that this is coming from the dipole radiation, that it just says that because since you have the dipole radiation, the merger will happen faster, the strain amplitude will change, and thus something like that. So this is a sensitivity. This is not, we did not use the real data. This is a sensitivity. Something like this you can probe. Anything above this line can be probed from neutron star merger. And if you have a neutron star black hole merger, then you can only have the dipole radiation. You can't have the force, right? Because black holes don't have muons inside them, right? And then finally, remember there was also a Yukawa force here. I talked about there's a Yukawa force, a new Yukawa force. If you use that and again do the strain sensitivity, now ideally for a neutron star merger, it has to be done both. We just did it separately. Again, this region is ruled out. Anything above is ruled out. There are a few hashed regions here that you see. These are coming from something called superradiance. I'm not sure it has been covered in the school, but superradiance basically says that black holes can form bosonic clouds around them, right? And that has been the fact that the black holes have not spun down. That gives you this region. These regions are ruled out, right? These things, and they are different at different. They are only at certain mass ranges because we can only do it for intermediate mass black holes, stellar mass black hole, and supermassive black hole. That's why there are only 3 mass ranges, right? And then the same argument that we talked about can also happen with binary pulsars. This is a paper which Subhendra Mohanty also wrote at the same time as us. In fact, he had an earlier paper long ago, where basically say that if you take the binary pulsars that people have measured, that timing is also just telling you something about GR. If you introduce a new force where it can rotate faster, things will go wrong, right? So that's coming here. So anything above again is ruled out. Again, whether it's a pessimistic muon fraction or an optimistic muon fraction. So this one looks a bit weird, simply because we took many pulsars and we just took the envelope, right? So it depends on which pulsar is giving. So the one pulsar is probably giving like this, other is giving like this, and things like that, right? Here there are some things, we think it's a numerical kink, and these things come because what is the final frequency that they can measure. All right, the bottom line is that, again, remember this entire parameter space besides these chunks were not probable. What is shown in this paper by us and also by Poddar et al. With Mohanty was that this region is ruled out, and also this region can in principle be probed using real data. So this is the same thing, except that we just did it for advanced LIGO and Einstein telescopes. The deconfiguration, again, we have the same thing. Obviously, you get better. How much time do you have? Yes. 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 From where will we get that? I don't know the answer, but from. Oh, I think we have used a bit. I don't know whether we have used it completely. Okay. Oh. Yes. But for that, we need both of them to be pulsars. Yeah, some of them are. Yes. From there, I'm just taking yes. Okay, yes. Okay, thanks. Yeah, so this, we did a bit, but I'm sure things can be done much better, as Kopu was telling. Okay. All right. So anyway, so bottom line, we showed that you can actually probe. Again, remember, in this whole white region is which we cannot probe, and this is a sensitivity. These are not real constraints. These are just sensitivities, right? And we are hoping to do something with real data with this. All right, 10 minutes. Okay, good, great. 3 talks, 10 minutes. Okay. So finally, I'll be talking about something which I've actually never worked on, but it's more fun. So this is how to search for dark photon, dark matter at gravitational wave detectors. So I talked about particle dark matter. I talked about long range forces from dark sector particles. Now let's talk about dark photon, dark matter. What is dark photon, dark matter? In simplistic terms, it's just a dark matter candidate which has a spin 1 vector boson, and it's extremely light. Typically, it's light, right? So one can show from various theoretical considerations that this is a good dark matter candidate. What does good dark matter candidate mean? Simply means you can write a full particle physics model, you can get the correct relic density, right? That's what it means here. And that region of parameter space is not ruled out. That's what I mean by a good dark matter candidate. But if you have that, think of it, so this is like a dark photon, right? So that means if standard model particles have this dark charge, right? So this obviously has some dark charge. If standard model particles have this dark charge, then what will happen is you can think of this dark photon, which is given by this A mu, producing a dark electric field. And if standard model particles have this dark charge, they will get affected by the electric field. Right? So effectively then the standard model particles have this dark charge, they will get affected in this dark electric field. Right? So let's denote the dark photon by this thing, and we assume that it is coupled to either E1b, this is anomalous, but let's forget that, doesn't matter here, or E1b minus L. So you can write down the Lagrangian, this is the standard kinetic term, except that this is the kinetic term in the dark sector. This is the standard mass term. Although these are dark photons, they are massive, and this mass can come from anywhere. We can take it to be Stuckelberg, right? And this is how the normal current will talk to this dark mediator using E. So this is the standard electric charge, and the epsilon that tells you what is the coupling of this dark sector to the standard model particles, right? So this is what the standard thing, dark photon mass. This is the thing. This is the strength. This is the thing. And you can show if this dark photon is extremely light, it can have an extremely long coherence length, basically given by 1 over mv, right? You put in the mass, you take some mass of 10 power minus 13 eV, v is 10 power minus 3. So this is the velocity of dark matter in the solar system. The coherence length is extremely large, right? So that means the entire range is sort of oscillating coherently, right, with the same frequency. So then you can write the dark photon field like this, and as I told you previously, what this simply means is any matter which is charged under this new force will experience this dark electric field. Once it experiences it, obviously it will have an acceleration, right? So the LIGO, Virgo, Kagra mirrors, it's made up of silica, the last time I checked. So this is the mass of the mirror. I mean, technically it is the mass of the point of the mirror. So here, whether it's E1b, then it will be all the baryons, or E1b minus L, then it will only be the neutrons. So there are some details here. And this is the force. The force is obviously the standard thing that we know from electromagnetism. You can just do this algebra, and the acceleration becomes this, right? So these are obviously, this depends on where is the position of the test mass. So that's the mirror, the two mirrors, mass of the total object, and this is the dark charge, this QD, right? So as I said, E1b, the dark charge is the total baryon number, and E1b minus L is the total number of neutrons. It doesn't matter, the result is roughly a factor of 2 different, right? But technically speaking, U1b is anomalous, so let's not, so we should be a bit careful. And I'm just saying it because this is what has been said by all of these papers, right? All right, now what happens? Now, so there are these accelerations, but the point is that the mirrors are in the L shape, right? So that means this phase, because of this xi factor, is not exactly the same in one arm of the L and the other arm of the L. And then there is a differential acceleration. What needs to do more precisely is take this thing, you integrate it over, well, you integrate twice, and then get the strain. You take the average and you get the strain, which depends on this epsilon, which, let me remind you, is this epsilon, which is the strength of the standard model particle and dark photon coupling, the strength with which it couples. Right? So this is one strain. The other strain that can happen is the fact that the entire object, remember the coherence length is about 1,000,000 kilometers. Right? LIGO is 4 kilometer by 4 kilometer. The entire object is in this 1,000,000 kilometer coherent, in this coherent bath of this dark photon. So it's sort of oscillating in the dark photon. Right? And that can give rise to a differential strain. Well, because by the time the laser light starts, hits there and comes back, the positions of the things have changed. So the time delay is a bit different, right? Because the whole thing is, because the two mirrors are getting accelerated in that time scale, in that light travel time. Because of that, you can have this sort of this common noise, which is slightly stronger than that. This was pointed out actually much later, after this paper. So the total strain that you can measure is this, and effectively this is like very similar to searching for a monochromatic gravitational wave signal. Right? It's not exactly same because there's a certain width, but it's roughly like that. So the LIGO-Virgo collaboration, LIGO-Virgo-Kagra collaboration, they did this search, and you can think of this as a direct detection of dark matter. You're literally probing how dark matter affects your instruments. And this is their result. Again, so let's look at this carefully. So the x-axis is the frequency, which is directly connected to the dark photon dark matter mass. right? And the y-axis is the coupling strength, is square, right? So anything above these lines that you see are ruled out. So this is coming, this is coming from this microscope experiment. Microscope was a space-based experiment where they had two masses, and they were just test masses, they were just floating in space, they were made up of different materials, and they were just testing Einstein's equivalence principle. And you can use this to test this kind of a long-range force idea. Anything above is ruled out. And then there's this Eort-Wash experiment, Eort-Wash-Washington experiment, where they were using a torsion pendulum. A torsion pendulum, again, you're testing the Einstein equivalence principle, basically like this, if you have a differential acceleration or not. But the same idea same observable can also be produced by this kind of a thing. And what LIGO did is LIGO did two analyses. One is the BSD. I don't exactly remember the details. And the other one is cross correlation. The fact that the coherence length of the wave is so big compared to the LIGO, and two LIGO detectors, you can cross correlate it, and anything above is ruled out in these things, right? So there are some kinks which, as far as I understood, they did not explain it clearly, at least I didn't understand. But anything above is ruled out. And these results are roughly consistent with each other. This result was for U1b coupling, but as I said, it does not matter because U1b takes all protons and neutrons, and U1b minus L, which is the more non-anomalous coupling, that is just neutrons, right? So there's just a factor of 2. So that's why they just did it for simplicity, just a normalization constant. Anyways, so I hope I've been able to convince you that gravitational waves can probe beyond the Standard model physics, and there are a large number of science cases. So I've only discussed 3 science cases: dark matter, nucleon cross section, there's new muon coupled force, and dark photon dark matter, and there are many others. Like for example, pulsar timing array. Pulsar timing array can also probe dark matter. I mean, Aryaman has worked on it. You can ask him. The bottom line is that these are promising cases for groundbreaking discoveries. Yeah, thank you. If you have any questions at any point, just catch me or send me an email. We're happy to discuss. Thank you.
Questions? Yes.
Yeah, so one of the questions I had was when you had the superradiance, hashed region in the previous one, this one. So this you are talking about the fact that if there is no force which takes away from the cloud, then the cloud will have a back reaction after it reaches a certain mass, and then it will stop the entire spin.
Yeah, this is a standard argument.
Yeah, the standard argument, right? But there could be non-standard argument based on the fact, like there are papers like Vitor Cardoso and all of that, as you know. So this will shorten, right, in that case?
Yes. The superradiance, obviously, so what you are talking about in some sense, what Indra is talking about are the back reaction effects which people have studied. And the way I said it, it seems that this is completely model independent. The reason is not, the point is not, and that's what, in general, that's what you're pointing out. In some sense, yes. So these things can, but okay, we just took something that is standard, and so that's it. We didn't do any other things.
And some part of this, then in your last talk, when you are talking about the LIGO, this one, some part of that will be here also, depending on the mass.
This is just LIGO's plot. Here, it can be there. I just took LIGO's plot.
Okay, because
so I don't know this, but 10 power minus 13 yes.
Yeah, that's what I'm saying. That is also in the same region.
Except that, remember, this is a vector particle, so you have to. So these. See, these are sorry.
Both of them are vector particles.
These are for vectors.
Yeah, that's what I'm saying.
Yes. Yeah, so but I just took. I mean, you can easily see it here.
Okay.
Yeah, so these are there. I just took LIGO's thing. I didn't modify the plot at all.
And I have more questions on the first one, but then we can discuss with you. And that's what I was thinking. Yeah, so thank you.
Knows better than me.
More questions? Yes.
Yeah, so I was curious, the black holes that formed due to this capture process, do they all form at the same radius, the nucleation radius of the black holes inside the neutron star? Are they?
Oh, no. So this, I think, Sulabna showed this thing. It depends on a few things. I mean, you mean the first black hole that was formed at the center, right? I don't think they have the same radius. They have slightly different radius. Please answer. Yeah.
Because in that case, if a black hole is forming under a critical radius,
so if you're talking of whether the black holes can, those small black holes can Hawking radiate or not, yes, it can happen. So this is in some sense, yes. But these are formed at these are very small masses. And then, but if they are parameter space at heavier particle masses, where the black holes are formed with such a small mass that they will Hawking evaporate even before it can eat up the star. That is there. Is there in one of these papers. And the people have also done it earlier.
One last question?
Yes.
You have a mic there.
I just wanted to connect two sectors of your talk. One was about the vector dark matter and other about the L mu minus L tau.
Yes.
If the vector dark matter is actually L mu minus L tau,
Yes.
then they will oscillate neutron stars, because not neutron stars as muons, as you said.
Yes.
And then there can be such in PTAs, because if you have two different neutron stars oscillating under the, so there's a paper with Arpan Height, I know is here.
Yes.
So we have a paper where you can probe the oscillations of the neutron
so that's
stars.
the NANO-Grav paper with Deptos and.
Yeah.
Okay.
Deptos,
yes. Okay, thanks. Yeah.
Does anyone have a quick last question?
Okay, if not, my email is there. Please feel free to email me.
Yes, let's thank Ranjan for the talk.
Thank you.